Hello everyone. So this is Vinay, working as an assistant professor in the Department of EC CIT Gubi. So in the today's session, we'll see how to draw a schematic of Cmos inverter, and we will try to observe the DC characteristics of Cmos inverter, and we'll do transient analysis of Cmos inverter. So that is nothing but we will see the waveforms of Cmos inverter. So in order to draw a schematic here, I'm going to use electric VLSI software. It's an open source software, so anyone can download and so we can work. So basically here we're going to use CMOS technology to design an inverter. So we all know even we can design inverter using NMOS technology, and even we can design inverter using PMOS technology. See, the major drawback of NMOS and PMOS technology is the power dissipation. So where the power dissipation is more in the case of NMOS and PMOS technology. So basically what happens, there is a leakage current flow in the case of PMOS and NMOS, like between source and ground and drain and ground. Because of that, power dissipation is more in the case of NMOS and PMOS technology. But in the case of CMOS technology, where we are using both NMOS and PMOS, the transistor, because of that, leakage current will be very less. Because of that, power dissipation is very less in the case of CMOS technology. So that is a major advantage of CMOS technology. So now to design an inverter, we need so one NMOS and PMOS. NMOS transistor will act like a pull down transistor, and PMOS transistor will act like a pull up transistor. So we'll see so which one is pull up and which one is pull down transistor later. Okay, so now let's get into this software. So we'll see like how to how to create a library, and how to drag components. So we'll see all your new library. So just click on new library. Let's give a file name. Inverter underscore demo. Okay, because I've already created Cmos Inv underscore demo. So click OK. We can give any name, by the way. You can see a library is created. Okay, and meanwhile you can see there is a option here. I'll just drag it. Yeah, so there is an option here. There is a pop-up message. You can see here electric messages. In that electric messages, you can check so all the actions you can check here. You can see just now we have created library, so it will display a new library Cmos Inv underscore demo created, so that it will display all the the things. Now so just go to CMOS inverter, right click. There we need to create a cell. So create a new cell, and here we are creating schematic. So you select schematic, just give schematic name. Let's give CMOS Inv1. Let's give underscore 1. Okay, so click OK. Now, so this is the area. So in this area we are going to construct a schematic of CMOS inverter. If you want to see grid, so for that you just press Ctrl G, so that the grid will going to display. So here we are going to place components, and so let's see. So there is an option here, components. Now as I told that to design CMOS inverter, we need NMOS and PMOS. So you can see here, this is PMOS. Just click and drag. Similarly, we need NMOS. Just click and place it here. Now if you see, if you double click, it will display width and length. So we all know, like the width of PMOS is greater than of NMOS. So here, suppose while doing schematic, it is not required, like no need to maintain this one, but while doing layout, so we should take care width of PMOS. There we need to maintain so width of PMOS is greater than of NMOS. So here it's okay, but still let us consider here. I'm just giving I'll just make 10. So this one I'll keep 2 only. You can see, just double click so that you can change width and length. So I'll just keep 2 only here. Okay. Then what we need, actually we need VDD and ground, then we need input, then we need output. So here, so this is VDD. Again, click and drop. Next we need a ground. Click here and drop here. Next we need input. So this is input and output. You just click and drop. We need output. Click and drop. Okay. So now you just align these things so that so the connection will become very easy. So now let's do the connection. So very simple connection, wiring connection is very simple. See, here I just want to connect. So this is the source terminal of PMOS transistor. It should be connected to VDD. Now what we should do here, you just left click and here right click. The connection is done. Similarly, the drain of PMOS, this is drain terminal, and it should be shorted with drain of your NMOS transistor. So for that, again, so you just click here, left click, and here I just want to short with respect to drain terminal of your NMOS transistor. So to short that, right click. Now you can see connection is done. Suppose if this is not aligned, you just move it. It is aligned now. So now this connection is done. Now the drain terminal the source terminal of your NMOS transistor, it should be connected to ground. So let's do that. Again, left click and here right click, and the connection is done. Again, the gate terminal of PMOS and gate terminal of NMOS should be shorted and it should be connected to input. So again, left click, right click, again one more time, right click. Yeah. So now this is done. So I've just shorted the gate terminal of PMOS and NMOS, and it should be connected to input. So now we should apply input to the gate terminal. Again, you select this, left click, then right click. So now the connection is done. So just shorted input. Similarly, output connection. Now again you select this. So here left and here right click. So I just shorted output with respect to drain of NMOS and PMOS. So now this is done. So now we should give names for these transistors. So this is NMOS transistor, this is PMOS transistor, and this is NMOS transistor, and this is in and this is out. So no need to give name for VDD and ground. Okay, so only thing is we should give names for NMOS and PMOS transistor and input and output connection. So by default, so the source is considered as VDD and this is considered as ground. No need to give a separate name like VDD and ground. By default it will take. Okay, and now let's see how to give name for PMOS and NMOS transistor. So for that, so you select, again right click, you select, go to tools, go to simulation spice, and you click write spice deck. Sorry, you select PMOS transistor, go to tools, then go to simulation spice, in that set spice model. Okay, so now you can see here there is an option here, spice model. Yeah, you just drag it and bring it to this side. Okay, now once again you select that spice model, go to edit. You can press Control I, so that it will open objectives, or else just a minute. Yeah, so it will directly open, or else what you do, you select this, go to edit, and properties, object properties. Okay, so here you type PMOS, capital letter I'll use PMOS, click OK. Now you can see here PMOS. Similarly, select NMOS transistor, go to tools, simulation spice, in that set spice model. Now there is a spice model here, you just drag and place here. Once again you select that spice model, go to edit, then properties, and go to object properties, you type NMOS, click OK. Yeah. So now in order to fit this particular schematic, there is an option called, just go to window, there you just select this option, fill window, so that it will display properly, so that you can see schematic properly. Okay, so now you can see here, so this is PMOS, you can place it here, and this is NMOS. Okay, now have given names for these two transistors. Now let's see how to give names for input and output connection. So for that, again you just select input, go to export, create export, in that you type in, so just giving that the source name as in, click OK. Similarly, you select output connection, go to export, create export, you just type out. Okay, now these things are ready now. So now what we should do, we should write a simple spice code. So let's do that. So to write a spice code, so let's select in the MISC, just go to MISC, and in that so there is an option spice code, select that and you just place it here. Now again you just click text, go to edit, properties, object properties. So here we are going to write a spice code for this particular what is that CMOS inverter. As I said that in the beginning, here we are going to do two different analysis. One is DC analysis, where we will see the DC characteristics of CMOS inverter, and another one is what, transient analysis, where so output is in the form of what is that like pulses. So waveforms we will see. Okay, so two different analysis we will do. So first we will see the DC characteristics, or I can say DC analysis. So now let's see how to write a spice code for CMOS inverter DC analysis. Okay, you select multi-line text, because we are going to write 4 to 5 lines. So for that you need to select multi-line text, and here if you want you can change text size also. Anyway, it is not required right now. So let's start now. I'll just explain, I'll just write down the code, and then I will explain how to understand spice code. Okay, So VDD, 0 DC 5, then V in 0, it's DC again 5, then here we are doing the DC analysis, so dot DC V in then 0 5, the change is 1 milli, then so here we need to include C5 text code, so I'll just click OK. So let's check that path. So for that I'll just open one more what is that library I've already created. I'll just copy, you can see here there is one option here. I'll take this dot include, this is what we need actually. So Control C, I'll just close it, and you just double click here, it will display, or else just go to edit, properties, object properties, and here you just paste it. I will just explain what is that. Okay, so now this is the code, spice code for DC analysis of CMOS inverter. Let's try to understand so what is this code. You can see here, so here we are just specifying a VDD, that means the name of the source is VDD, and so the second VDD, that stands for positive, it's a positive, and 0 indicates negative. You can see, so this is actually 0, that is nothing but a negative, I can say. And what type of source it is DC source, and what is the value of this DC source, it is 5. So first line the name, the second one is positive, third one is negative, what type of source it is, whether it is DC or AC, it is DC, so I have just selected here DC, I have written DC, and how much voltage we are applying, it's 5 volt we are applying. And the second thing is what, the input again, so input again, so what is this input, the name. So this, the first one indicates what, the name, second one indicates what, it is positive, and again 0 indicates negative, and again, so this is again what type of source here, it is DC, and how much voltage we are applying, it's 5. Now what type of analysis we are doing DC analysis. Whether you do DC analysis or AC analysis, always we should start with the dot. So dot, so this indicates we are doing DC analysis, and here so I'm just giving the value, so input should vary from 0 to 5, and so this 1 milli indicates that is a change. Okay, so then this is the name, the there is an option C5 underscore models dot txt, so where, so what, how much the rise time, fall time, then the all the parameters are available in this particular C5 underscore models. So this we need to select. Okay, so this is mandatory, so we must give so this particular we should consider this particular what I can say C5 underscore models. So next click OK. Okay, so now, so let's check whether any errors are there or not, like so for that we need to check that DRC. So there's an option called DRC, so in that check hierarchically, you can see here. Yeah, so we got actually one error. Let's see that. So to clear that, you just go to edit, there's an option called cleanup cell, cleanup pins. Okay, now once again go to tools, DRC, check hierarchy. So now you can see here 0 errors, 0 warnings, 0 warnings found. So as I said that, so it will going to display all the messages. Okay, so now let's check the simulation now, simulation part. Go to tools again, then simulation spice, write spice deck. So here So go to visible traces, this option, pick visible traces. There we need to select input and output pins, input and output ports. So for that you need to select this, and we need to select V in and V out, click OK. Okay, you can see here so let's compare and we'll try to understand. So no need to use a separate plot. So let's combine input and output and we will analyze. This is our input and this is our output. You can see here when the input is 0, output is actually 1. I mean output is high. See what is basically inverter. So it will going to invert the input. Suppose if I apply 0, output will be 5. Suppose if I apply 5, output will be 0. So that clearly indicates here. You can see when the input is 0, what is the output? Output is 5. When the input is actually high, you can see the output is actually 0. Okay, so this is the DC analysis of CMOS inverter. I can say the DC characteristics of CMOS inverter. Okay, so now let's see a transient analysis of CMOS inverter. So where we will give input in the form of pulses, so that we can see the waveform, output waveform. So I'll just close this. Now just close this. Okay, now let's do some modification in this spice code. So once again, select this, go to edit, then click property and click object properties. So here let's do some changes. Once again, I'll just explain. I'll just make changes. Now what type of analysis so we'll do now? It's transient analysis. So for that, input should be in the form of pulses, right? So now let's change this one input. So I'll select this one as it is, because whether it may be DC analysis or transient analysis, we must give VDD and ground. So this line I'm not going to change. So now coming to the second line here, we should change. So input, again this is same, beam, the name, then so it's positive and this is negative. And now what I'll do, I'll just change this. It's negative and it should be now in the form of pulse. You write pulse. So pulse, then 0. It means it should vary in between 0 and 5. Okay, the next 3 zeros, and that indicates the first one is the delay. So first 0 is delay, the next 0 is rise time, the next 0 is the fall time. So next the width, the on time and off time width we need to select. So for that you can select any value. I'll select 5 nanoseconds, and one more I'll select 10 nanoseconds. So this is 5 nanosecond is the on time width and 10 nanosecond is the off time width. Okay, so here please check this. We need to check the waveform now, and here we are giving input in the form of pulses, and that is the reason here I'm using word called pulse. Next, what type of analysis we are doing? Right now we are doing transient analysis. So for that, as I said that whether so we do DC or transient analysis, always we should start with the dot. Now here we are doing transient analysis. You select tran, 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 and up to like 100. I'm just selecting 100 nanoseconds. That means it should run up to 100 nanoseconds. So it will go into the transient analysis will do up to 100 nanoseconds, 0 to 100 nanoseconds. Okay, so now click OK. Now once again we need to check errors. Go to tool, DRC, check hierarchy. So you can see 0 errors and 0 warnings found. Now again go to tools, simulation spice, right, spice deck. Yeah. So now here again, so to we need to select ports here. So for that there is an option here, you can see waveform option here, pick visible traces. There you will find, there you need to select ports. You just click, select V in, V out. You need to observe both input and output, so you just click OK. Now you can see here, so the waveform is actually displaying. So it is overlapped actually. So in the previous case, we just overlapped input and output, so that we can easily analyze when the input is 0, output is high, and when the input is high and output is 0. So here if you want, you can split. So for that, what we should do, right click. So there is an option called add plot pane, add plot plot plane. You select that. So the one more plot is added. Now what you should do, so here I'll just move in to this plot. Okay, now you can see here, when the input is high, output is 0. When the input is 0, output is high. Okay, so this is all about transient analysis. Okay, thank you.